Let's talk about the topic on two's complement real quick. And it's just an extension of binary. Yeah. Binary, we're still talking about number systems, of course. Number systems. So up to now, we have been quite comfortable with converting a number from denary to decimal, right? From denary to decimal. We've already been comfortable with doing this. That's at the from denary to binary, I mean to say. From denary to binary, because denary is also decimal. Right? To binary. Let's say a number like, let's say 40. If you are asked to convert this into binary, we say that we're going to use the number line 1. We suppose that we are putting it into 8-bit, yeah? If you're putting this into 8-bit, we have 1, 2, 4, 8, 16, 32, 64, and 128. 1, 2, 3, 4, 5, 6, 7, 8 bits, yeah? Like this. That's our number line that we're going to be using for that. So to have a 40, we need a 32 and we need an 8. Everything else becomes zeros. That's basically what we need to do. I'm pretty sure that you're already well acquainted with this. When talking about two's complement, this comes through handy whenever we want to represent negative numbers, or let's just say signed numbers. They used to represent signed numbers, right? Signed numbers. So we're talking about the number that I have a positive numbers and negative numbers, of course. So here, with this natural binary that we already used to, we cannot present negative numbers. Like let's say negative 40. If we're asked to present negative 40 here, we just cannot, because there is no room for us to input negative numbers here. Yeah, but when we talk about the part of two's complement, it allows us to represent signed numbers, either positive or negative numbers. What's the trick? The trick is pretty simple. What we just got to do here is use the same number line here, but the most significant bit here, the one that is at the leftmost, is supposed to be coming through as a negative number. You get the point? So I'm saying I have 1, 2, 4, 8, 16, 32, 64, and I also have 128. But as I said, the most significant bit is supposed to be coming through as a negative number. So this gotta be a negative number, such that whenever I'm representing a negative number, I know that I need to take this as well. So one thing that I'm already seeing is that for two's complement, if the most significant bit, which is this one, or we can call it the left most bit, the most significant bit or the leftmost bit is supposed to be 1 to indicate that the number is a negative. This is for negative numbers. So I'm saying here already I have negative 40, which means I need a negative 128. So what else do I need to add to negative 128 to get negative 40? So I'll use my working space that I'll be giving in the examination, that negative 128, oh come on, let me take you a little bit to math here. 128, right, plus x should give me negative 140. Oh come on, should give me 40, negative 40 like this. So I'm saying x, I want to find the value that I'll add to negative 120 that I've already taken to get the value of negative 40. So it's x is now equal to 128 less 40. If I subtract that up, I get x being equal to, is it 90? No, it's 88. Right? So I need an 88 for me to be able now to get a negative 40 at the end of the day. So negative 128 plus 88 gives us negative 40. So how do I get now 88 on the numbers that are positive that are remaining here? I need to get 88 from there. So I need 64 definitely, right? If I take 32, I'm going to be getting to 90s. I don't need this. But if I take this now, I'm not going to be going now to what? I'm not going to be going to 80. So I need 88. So this is my 8. Everything else becomes 0. So this now in its two's complement is negative. Oh, come on. it's going to be coming through as 1 as my most significant bit. 1 1 1 0 1 1 0 0 0. This is my 4-bit representation of negative 40. Check this out. The most significant bit is supposed to be negative, and indeed my most significant is supposed to be 1, and indeed my most significant bit is 1. I hope that makes sense. So let's take the part on if we need a positive number. A positive number now in its choose complement is the number again in its binary state. I hope that makes sense. A positive number in its choose complement doesn't change. The binary representation of that number is the same value that you're going to be having here. Let's just try that out real quick. We are saying negative 40. Let's now take about positive 40. Positive 40. If I'm talking about positive 40, let me just change my ink here so that I can just present using the same dish. If I'm talking negative 40, if I'm talking about positive 40, definitely I don't need this, right? So already I'm now seeing that for positive numbers, right? For all the positive numbers, my most significant bit or my leftmost bit is supposed to be coming through as 0. This is for all the negative numbers. So we're coming through with our 0 right there. Then we need to get a 40, so I need this, and I also need this. Everything else becomes zeros, like that. So negative 40 is going to be coming through as, positive 40 is going to be coming through as 0, 0, 1, 0, 1, 0, 0, 0, because I only need 32 and 8. Check this out. The same number that I got here is the same number that I had here. 0, 0, 0, 0, 1, 0, 1, 0, 1000, 1000. So that's basically what you have. The number, a positive number's choose complement is the same as its primary binary number. That's basically what we have. So that's basically how you convert numbers to their choose complement. Maybe a couple of two more examples before we close this up. Let me just change ink here because I'm seeing that blue is not quite the color. Okay. So let's talk about more examples. So let's talk about negative 120. Let's talk about negative 78. Let's talk about positive maybe 34. Right? So with that now, I'm still going to be using my number line. I'm going to be putting these in their 8-bit choose complement. It's 8-bit choose complement. Right? That's what you want to do. So we're coming through now to say that we're going to be using our 8-bit representation like 1, 2, 4. Oh, let me just use the foreign space so that I can just easily do that. So it's 1, 2, 4, 8, 16, 32, 6, 4, and negative 1, 2, 8. Like this. Right. So with this now, we want to get negative 120, and we say this now needs us to do a couple of workings. We are saying to get negative 120, we are saying negative 180. Oh, come on. To get negative 120, I'm saying negative 128 plus x should give me negative 120. So we're saying x is now equal to 128 minus 120. So my x is equals to 8. So I now already know that I need to take this one definitely, but I need to get again an 8 as a positive number because these are my positive states. So I'll get a positive 8 and negative 120. Everything else becomes zeros. Then I'm done. This is how I find my negative 128. When you're talking about the next one, it's a negative number again, so I need to do my small working real quick, right? I will say 128 less 78, right? So I'm saying here, I need to say negative 128. Let me just change some of my color here. Let me take red. Negative 128, right? Plus x is equals to negative 78. So my x is now equal to 128 less 78, which is going to be giving me a 50. Yeah, so I definitely need this, and I also need a 50. So I'll get 32. 32 plus 16 is going to be giving me a 48. So definitely I need this. 48 plus 2 now gives me a 50. Everything else becomes zeros. Right, that's basically how I solve this. And the last part was now for the part on 34. So if it's positive 34, we already agreed that the most significant bit gotta be 0. Yeah, and for 34, you need 32 and 2 for the positive numbers. These are positives. This is the negative, the only negative. So this is all, these are all zeros. That's basically what I have. So this is going to be giving us this, and this just came through to give us this, and this gave us this. That's basically how we convert numbers from their decimal state to 2's complement. So there's another way now of doing this that involves the first part. But rather, I'm not going to be teaching you that one because I already feel it is long. So this is how you solve numbers as far as 2's complements are concerned. If you have any question, please touch base with me. Then we'll talk about them. Yeah.